Okay, so I'm happy to introduce Sean Linden, our speaker today. Sean is a postdoc at UMass Amherst working with Daniela Calzetti, but you'll be moving soon to University of Arizona, right?
Yes.
So he'll be a bit closer to us in Tucson. Sean finished his PhD at University of Virginia in 2020, and I don't know if there's a wavelength of light that you don't use in your studies.
Yeah.
So,
over the years, I've used quite a few.
From radio to X-ray, and Sean is an expert in studying star formation and massive clusters, and he's here to talk to us today about the most massive clusters in some of the most extreme environments in the local universe, and work he's done with HST and JWST. So take it away.
Thanks, Jeff, and thanks to the organizers for having me. It's a pleasure to be in LA, actually my first time in Pasadena, so I'm very excited to be here and just really enjoying, well, maybe not the cold weather, but everything else has been really great so far. So like Jeff said, I'm going to talk about young massive clusters in extreme extragalactic environments. And to motivate a little bit why we care about these kinds of environments, I start by looking at a plot that I'm sure everyone is very familiar with, which is the Maddow and Dickinson 2014 plot showing the density of star-forming galaxies as a function of redshift. And if you look back in time, you find that at around a redshift of 2, there's a characteristic peak, which we call cosmic noon, where the majority of the star formation activity in the universe occurs. And actually, with ALMA, we've been able to understand through work from Nick Scoville that this increase in star formation activity, which you see here in the blue, is due to a combination of both an increase in the ISM gas density of galaxies and the star formation efficiency of converting that dense gas into stars. And so you can see that from today to cosmic noon, not only does star formation increase by 10 to 100 times, but you get increases of up to an order of magnitude in efficiency and gas density. And so these galaxies that are the main sequence at high redshift, they really don't look anything like a sort of Milky Way-like galaxy today. And to further show that, on the left-hand side, I have a compilation of nearby galaxies that I put together using sources from the PHANGS and LEGUS collaborations, which are these large multi-wavelength campaigns studying star formation in nearby galaxies. And you can see that looking at them, they essentially form a nice tight sequence, which is essentially the local universe star formation rate main sequence. And in orange, I'm actually plotting all of these systems from the Great Observatories All-Sky LIRG survey, which is a sample of the 200 brightest infrared bright galaxies from the revised bright galaxies sample. And GOALS has actually followed up these 200 with observations of the complete sample with Spitzer and Herschel, and for many of them also additionally Chandra, HST, VLA, and some ground-based observatories like Keck, and some JWST stuff that I'm going to talk about in a little bit. And so you can see that the globally integrated values for luminous infrared galaxies, again, they are an order of magnitude above the local sort of star formation main sequence. And if we break down these globally integrated values into individual star forming clumps, we again see that compared to sort of resolved nearby galaxies from SINGs, these sort of black points here, luminous infrared galaxies and GOALS, the clumps that we observe with HST near infrared Passion beta emission, shows that these clumps for the same size have star formation rates that are 1 to 2 orders of magnitude higher, and actually in a resolved sense are consistent. Some of the most massive clumps in LIRGs are consistent with some of the results of these lensed high redshift studies that can really magnify individual galaxies and sort of resolve individual clumps. And so the point here is that luminous infrared galaxies in the local universe are a laboratory for studying the kinds of ISM conditions that we find abundant at higher redshift. And that's not to say that all of the high redshift galaxies look like LIRGs. It's not that they evolve essentially like local LIRGs. It's that the local LIRGs are the only places that we find where the ISM conditions match those of higher redshift systems, and where we can actually study these things in great, great detail. And so what do GOLS galaxies look like? Well, I sort of alluded to it, but many of them are actually nearby major mergers. And so here's just a montage of Hubble Space Telescope images of the GOLS sample. And you can see that they span a wide range in merger stages, in dust obscuration. There's a wide variety here. And the point, sort of one of the goals of my research is to understand how these intense extreme environments that are molecular gas rich, how does that affect the formation and evolution of their individual star forming region? So, that is sort of where my research has led over the last 6 years. And for a little context, I want to talk briefly about one of the most well-studied nearby major mergers, which is the Antennae galaxy. And so what do we actually know about star cluster formation from a prototypical merger? Well, we find that, firstly, if you look at the star cluster age distribution, you find a very steep power law in the dNdt, which they associate to the fact that there's a lot of cluster destruction. So based on the slope, 90% of all star clusters that form in the antennae are destroyed for every order of magnitude increase in age. And not only that, but mergers also appear to drive cluster formation to even higher masses. So here's a compilation done in 2010 by Soren Larsen, where he looks at the mass functions of star clusters in various nearby galaxies, including the LMC, M31, and M51. And you see that the antennae actually lives well above to the right of these sort of other well-studied sort of either dwarf galaxies or more normal Milky Way-like star-forming galaxies. So the conclusion there is that mergers appear not only to be destroying clusters, but they also seem to be forming them at much higher masses than what we see in the Milky Way. And actually, this isn't just seen observationally. Simulations as far back as 6-7 years ago show that Milky Way-like merging galaxies produce these very massive clusters with masses on orders of 10 to the 6, 10 to the 7. And it's these extremely high pressure regions of the ISM which lead to these extremely massive clusters. And you only get these kinds of extreme pressures and densities because of the active merging environment of LIRGs in the local universe. So to study the star clusters in these systems, we undertook a survey with HST using to look at 10 galaxies with HST WFC3 U-band observations, which actually we were forward-looking in that we chose galaxies that were either going to be in the JWST ERS or the approved GTO targets. And so you'll recognize this actually is the title slide was actually a NIRCam image of this galaxy. So you'll get to see some of the differences between the NIRCam image I showed and actually this galaxy is the other one that I'm going to be talking about at the end. So here's actually what the multi-band HST images look like. So when you're looking at these are the sort of near UV, and then the two on the right are the optical. And you can see, especially in the case of both of these galaxies, actually, there's nuclei hidden underneath the dust in both. So there's a nucleus completely obscured in the eastern component of VV114, IC1623. And similarly, in NGC 3256, there's an entire nucleus completely hidden behind dust in this system. And so we've never, even with HST, all of the bright clusters that you see in these images, we're still completely missing all of the activity going on in those dust-enshrouded nuclei, which we will now finally get to reveal with JWST. And these circles actually show that because we have such a rich suite of multi-wavelength data in the infrared, we're actually able to measure using 2D spectra from Spitzer, actually what the size of the mid-infrared cores of the galaxies are. And so we're able to also spatially break clusters into things that fall sort of within the central mid-infrared bright regions of the galaxy, and then outside of that to look at and see if there's any differences locally within LIRGs, not just globally relative to other Milky Way-like galaxies. So here's sort of some zoom ins of what cluster detections look like in these things. So I'm just zooming in on 3 different portions of the bright optical part of the disk in VV114. And you can see that the clusters that we pick out are essentially these brightest, compact regions within the galaxy that all essentially are well detected across all 3 of those HST bands that I showed you. And we then perform a set of SED fits using different models, different grids of dust attenuation law. And I'm happy to talk about some of the details of that if you're interested, but I'm going to sort of skip over that and just say we use this multi-band imaging to derive ages, masses, and extinctions for every single star cluster that we detect, and the examples of that are shown in those blue points. So coming back to this DNDT diagram that I mentioned before, where I was showing some of the data for the antennae, the way to think about this, I just like to show this cartoon, is that if you have star clusters forming in a galaxy with no evolution, such that none of them are being destroyed, you might see something in blue, where you sort of have a steady state DNDT. If you then take that steady state and you add a contribution from destruction, and that cluster destruction comes in multiple flavors. So you can have early evolution. So star clusters can be unbound and destroyed based on photoionization, stellar winds, supernova, things that happen in the early evolution of a star cluster. And then you get things like evolution within the tidal field, collisions with passing giant molecular clouds, tidal shocks. And these things are expected to operate on much longer timescales, of hundreds to millions of years to gigayears. And then, of course, long-term evolution, the clusters will evolve with 2-body relaxation, and the clusters will sort of slowly lose mass. And this happens over a long time period. So all 3 of these things work to take the curve in blue and turn it into the curve in red. And we try and use this simple formalism to understand what the dominant mechanisms are at play at various regions, age regions within these systems. So here is some data from that program of 10 galaxies. So here I'm just focusing on 3 of the most cluster-rich systems, which were the 2 galaxies. 2 of the 3 galaxies in that were what I showed you, VV114 and 3256. The other one is actually NGC 7469, which is another GOLS ERS program. But essentially, when we look at the data from those 3 systems, and we then break the sample from those 3 galaxies into things that fall within the mid-infrared core or outside of their respective mid-infrared cores, we see that this sort of simplified picture with the antennae, where everything looks very, very steep, is actually a little bit more complicated. We find that in the central regions of the LIRGs that we studied, we again find this very characteristic steep slope, which we again associate to a significant cluster disruption, similar to what we find in the antennae. However, when we look in the outer disks of these LIRGs, we find that the age distributions look much flatter. And that tells us that the star clusters there in those regions are evolving much less chaotically. There's much less going on to unbind clusters. The tidal fields are significantly lower. And you also have collisions with giant molecular clouds, which are going to happen much, much less often. And the reason for that is because luminous infrared galaxies, being major mergers, tend to funnel the majority of their material into the central regions in a very efficient manner. And so you can really crank up the GMC surface density and ISM volumetric density really high, which then allows you to produce a timescale, a characteristic timescale for shocks, tidal shocks, that is consistent with essentially driving this increase in the slope from the outer disk to the inner disk. And so we argue in the paper that it's these collisions with giant molecular clouds that is one of the, in the extreme centers of LIRGs, that actually work to change the cluster disruption function from something maybe more Milky Way-like, or in this case, the example shown is M83, to something much more antennae-like in the central regions. And actually, this has also been seen in simulations. So Zoom-in simulations from Smuggle actually show that for clusters of around a mass of 10 to the 4, one of the things that is working to flatten the mass function as the merger progresses, so the merger progresses from blue to red here, the overall mass function gets flatter and flatter, which they actually attribute to the strong tidal fields in the center of the galaxy that work to unbind and remove star clusters. And so we're actually seeing observational evidence of the things that are now being reproduced in sort of high resolution hydrodynamic simulations. So I do think that there's a lot of synergy between the sort of broad results that we're getting in the optical and what now the simulators are finding. And so that's really exciting. And just to point out, the sample wasn't selected to have an even, for this paper, we didn't have galaxies that nicely spanned every single merger stage. So there's only 2 late stage mergers in this sample of 10 galaxies. But from that preliminary analysis, we do actually find that the late stage mergers look like they have a shallower mass function than the sort of early stage mergers, being if you compare the 2 values in red there. And there's 2 fits here, both for power law and sorry, go ahead. Yeah, so the question is how do we determine the merger stage? In goals, because of the suite of multi-wavelength data, the merger stages often are determined in multiple ways. But there's a couple of papers that looked at essentially Spitzer imaging and HST imaging to look for tidal tails, look to see where the galaxies fall in projection, look to see if there's multiple nuclei visible in the near infrared. And so all of those things together, it's mainly how many nuclei, where they are, and do you see significant tidal features. So like a late stage merger would be something that looks like probably a single nucleus with sort of tidal features outside. And a mid-stage merger would be 2 very clearly resolved galaxies. And in the case of the ones I showed you, VV114 and 3256, even though in the optical we only see 1 nucleus, we know that there's 2 nuclei there, and those 2 are in sort of the mid-stage of final coalescence. So I just want to briefly take an aside to highlight some of the work that I've done really recently since I've been at UMass. And this is just that we find that this variation in the age distribution slope is not just something that we see in luminous infrared galaxies. So while it's a much easier thing to find there because the extreme contrast in gas and surface densities, with deep enough and wide field enough data in even normal spiral galaxies. So here, this is HST YMC-3 ACS data as part of LEGUS, where we actually sampled the entire optical disk of M101 from the sort of central regions all the way out to the outskirts, where you can see from this false color image, there's very little star formation happening. And here I'm actually showing in purple and red the histogram distributions of the star formation histories of M101 based on the resolved color magnitude diagram. So resolved CMDs of individual stars work to actually produce these star formation histories. And the point that I want to make by showing them is that it isn't the case that the star formation history is actually the same as the cluster disruption rate. So you might worry in something like this that if the star formation history had the same slope as the cluster destruction rate, then we're not seeing cluster destruction. We're just simply seeing preferentially that there's much more star formation happening at early times today. So the fact that we see flat or even increasing star formation histories shows us that these negative slopes in the central region, in the southeast, and in the northwest actually is due to this cluster destruction. And for, there's not many galaxies that are nearby that we've studied with this level of detail. For M101, we actually had 40,000 sources that we detected in HST. And we actually have to have humans look at that. Yeah.
The distance from the galaxy center to be considered outer star formation history, center star formation history?
Yeah, so the center star formation history essentially covers the inner 4 or 5 kiloparsecs, and then the outer star formation history is focused on this sort of outer 10 to 12 annulus. So in the paper that that we derive those from, they do it in sort of annular bins. So we take the middle annulus and sort of the outer annulus as our two cases for these two curves. So, obviously having humans look at 40,000 sources is crazy. And so we're in a regime very much so, and this is true with LEGUS, this is true with PHANGs, any nearby galaxy survey studying star clusters now relies heavily on machine learning to actually create a training set of humanly classified sources and then use the machine to classify clusters throughout the entire galaxy, as opposed to having a poor grad student look at every single one of those sources. And for the handful of galaxies that we've done this for, we actually do find that the gamma, there's this slope here, actually seems to increase as a function of the gas surface density. So again, we argue that it is this sort of gas surface density or the density of the ISM, these collisions with GMCs that ultimately help to shape the sort of intermediate term evolution. Because you see here that for all of these age distributions I'm showing you, we're not fitting these two youngest bins. And the reason for that is because it's very difficult to tell if clusters are bound or unbound at the very early ages. So it's very difficult to interpret the slope in that regime. The other problem, of course, is that we rely on UV data, and UV data is not sensitive to dust-buried sources. So if we really want to be confident that we have all of the sources detected at less than 10 million years, we have to be really confident in the depth of our data, and we know that we're missing a lot of the youngest, most dust-buried sources by requiring detections in the UV, which we do in order to get accurate SED fits. So that is why sort of all of this is focused on this intermediate term evolution. But I do think that we're finding lots of observations now that support this scenario being essentially driven by the density of the ISM. And so I've been alluding to it a little bit, I just did, is if we really want to understand sort of the next step of this process is to understand the earliest stages of star cluster formation. And so I put a question mark here because even more so in the luminous infrared galaxies, with M101, it's not nearly as dusty as something like a LIRG, so you're really not missing nearly as much. With luminous infrared galaxies, we felt going into the ERS that we would probably be missing a lot of the star clusters that were deeply buried that we completely missed, especially surrounding those completely enshrouded nuclei that I pointed out in those two galaxies. And if you look at just GALEX data of the GOLS sample, we find that relative to the infrared emission, the far UV misses 80% or more of the total star formation. So a significant portion of the UV misses a significant portion of the total cluster formation that must be happening based on the infrared emission. And so the goal here is, now that we've used HST to sort of demonstrate how LIRGs affect this sort of intermediate term evolution of clusters, we can now use JWST to understand how these extreme environments are affecting the earliest stages of cluster formation. And again, why we might want to do that? Well, there's been a lot of work as part of the PHANGs collaboration and others that is now starting to pull together all of these multi-wavelength data sets using tracing essentially different stages of an embedded star cluster's life. So if you say you start with molecular clouds, some of them are not forming clusters, and then of course some of them will have a very, very newly born star cluster embedded within them. Then as you go to sort of H-alpha, CO-H-alpha overlap, which is sort of shown in red here, you start to get this emergence phase where the cluster is the early evolution from photoionization, stellar wind, supernova, is pushing the gas and the dust out of the giant molecular cloud, exposing the ionized gas nebula for us to observe. And that is why the H-alpha observations sort of kick in here. And then you get to sort of exposed star-forming regions, which are essentially H-alpha or optically bright clusters that you detect that can have ages of hundreds of millions of years, or giga years or more. And so they use these spatial correlations of these different tracers to sort of represent different phases to find that this embedded phase of cluster formation as the cluster is emerging from its cocoon does seem to vary in different galaxies. And this is a sample of, a handful, 10 or so. So it's not clear even from these observations what is causing that variation. Why do we see certain galaxies take, the clusters seem to take a lot longer to emerge from their environments as opposed to something like NGC 5068. So this variation and these variations lead one to believe that different early feedback mechanisms actually work to sort of affect the ISM in different ways. And another visual representation of that is from this compilation by Mark Krumholz in 2020, where he takes observations of star clusters and just plots their radii and mass. And the hexagon bins are Milky Way observations, M31 data from the FAT survey, and then NGC 628, which is actually early results from LEGUS here in sort of green hatches. And then he overlays a couple catalogs of M51 in the Milky Way. And what I want to focus on is these purple and green symbols, which are these superstar clusters detected in these two nearby starburst galaxies. So M82 and NGC 253 are two of the most nearby starburst-driven sort of galaxies that we know of in the local universe. And the clusters that form at the center of both of those systems are incredibly compact and incredibly massive. And so you see here, these sources that are forming in NGC 253 and M82, they have masses for their size that they're the only really comparable to these globular clusters in the Milky Way and M31. And the way to actually read these lines is that each one of these represents a different early feedback mechanism. And the effectiveness of that mechanism to unbind star clusters means that the source lives to the left of the line for all of them except for the direct infrared radiation pressure. So the direct infrared radiation only can unbind clusters that live to the right in this lower region. And so we basically have found no examples in the local universe of things at 10 to the 6 with a radius of less than a parsec. If they exist, we haven't found them. They might, and they would be really interesting to study because this is where this feedback mechanism is likely to dominate. But one of the things that's interesting about this diagram is this region of white space where really none of these feedback mechanisms seem to be effective. And it's interesting that the majority of these incredibly compact, massive star clusters that we find in these starburst galaxies live in this regime, which means that likely, if they are not going to be unbound by their environment, these are sources that have a very high likelihood of surviving their early evolution and potentially living to become the globular clusters, not necessarily the ones that we see in the Milky Way, because a lot of those are accreted. But essentially, the idea is that star clusters that form in the early universe, some of them have to survive. They have to survive to today, or we wouldn't see globular clusters in and around the Milky Way. And if you think that M82 and NGC 253 represent starburst conditions of higher redshift galaxies, then the fact that they fall in that regime suggests that those are things that would have been born, in a high redshift analog. They'd be born at early times, and they would live likely to the present day. And so what we're hoping to do in goals is to populate this diagram with super young sources that we've not been able to do before this, see where they fall, see which feedback mechanisms are mostly affecting the clusters that we find in these LIRGs, and can we say anything about how they compare to these other nearby starbursts and normal galaxies? So finally, that brings me to the Goals JWST Early Release Science Program. So this was 4 galaxies that we were awarded time to study with most major instruments on JWST, not every single instrument, but we used NIRSpec, the MRS, NIRCam, MIRI, and subarray imaging. So we have, imaging and spectra of all 4 of these galaxies from, 1 to 20 migrons. And I kind of joked in the beginning, actually, all 4 of these images are amateur astronomers or space enthusiasts who are much, much more talented with Photoshop than I will ever be, and actually produce these amazing NIRCam false color images of the 4 systems. So NGC 3256 is and VV114 are the 2 that I've already talked about. And you can see, and I'll show a close-up comparison of that, the one on the right in a second. You can see just coming to 3256, this nucleus here is the one that was optically visible. And this secondary nucleus down here was completely hidden behind dust in the UV, is now, totally unobscured in the near infrared. And we can study all of the clusters that are forming, and there are lots of clusters forming in and around this nucleus. Zwicky 96 is another kind of odd galaxy. It's actually not clear how many individual galaxies are merging here. Some people think it's a triple merger. Some people think it's a double merger with this sort of crazy region. But the reason that this galaxy was chosen for the ERS is because this region here is one of the most compact infrared bright regions that we've ever seen in a nearby galaxy. I think it's like 2 orders of magnitude in infrared surface density higher than the Orion Nebula. So it's an incredibly dense, compact region. And it's been a debate for a very long time whether or not this is just a very, very embedded AGN. This was some sort of single or collection of very massive star clusters, maybe even top-heavy star clusters, given the total luminous output. And actually, the MIRI data the imaging data was actually relatively inconclusive for what is actually the main power source. So the spectra for this system, which ideally will give us the definitive answer of if this thing is an AGN or a really bright, massive collection of star clusters, that is actually data that's being worked on as we speak. But even from the mid-infrared imaging alone, it actually was very unclear what is actually powering that source. The 4th galaxy, and I highlight it here because I'm really not going to talk about it at any more point after this. The reason that this one was chosen is because you can see from the PSF is this is a bright Seyfert nucleus at the center here. And actually, it's hard to tell, but NGC 7469 has a really close circumnuclear star-forming ring. And so the idea with 7469 is that it's a galaxy that allows you to study the connection between black hole growth, AGN feedback, and star formation. And so there's lots of great work by Vivian Yu and Thomas Lai that's already been published on this source, but it's a lot, again, focusing on the black hole, the outflows. And so I'm not going to talk about that here, but I'm happy to talk about it afterwards as well. Okay, so a little bit more of a close-up on VV114. Here is actually some ESO press release images of the galaxy in optical UV. So this is the sort of the same image that I've been showing with the eastern nucleus totally obscured in the bright western galaxy, where again, all of these point sources is the clusters that we've already detected and characterized in that paper that I showed you. And now moving to the near infrared, we see that this eastern nucleus actually in the full array images is completely saturated. It's very bright. All the dust that surrounds it is essentially gone. You do see that there's lots of hot dust that weaves its way through the center, the overlap region of the galaxy. And so it's this sort of overlap region where all this hot dust is, in addition to the nucleus, that we detect essentially all these sort of new infrared bright sources. And just as a comparison of NIRCam to MIRI, one of the things that surprised us, or at least it surprised me, with MIRI is that when you go to even longer wavelengths, again, you see in red all these massive star-forming regions, and then again, the nucleus is completely saturated. But what you see in blue here is actually the MIRI F77W image, which is tracing the 7.7 micron pH, which means that there's an incredibly large amount of diffuse pH emission that's either been the dust has essentially either been ejected from the galaxy or ionized, outside in these diffuse structures. So it's not clear actually how all of that pH is getting out there. But if you look at the total contribution of the 7.7 micron luminosity, there's a significant contribution from this diffuse component that before JWST, we didn't know existed at all. With Spitzer and Herschel, we couldn't resolve or detect this diffuse component. We had no idea that it was there like this. And so this is maybe a ubiquitous thing in nearby mergers. You see this diffuse pH emission surrounding in the halo, but I thought that that was a really cool kind of result from some of the early rounds of papers. Okay, so maybe to just hammer home the point that I'm trying to make, I made a little movie of the HST to JWST comparison. And again, we see nothing, then we see the nucleus completely pop up. But what I want you to also focus on is this region here. And it sort of weaves its way through the galaxy. All of these regions and the sort of the hot dust that surrounds them, we completely miss them in our HST studies. And so with the NIRCam, just a couple numbers, with the F150, 200, and 356W imaging we got with the ERS, we identified 374 compact star cluster candidates, and 20% of those candidates are actually completely undetected at optical wavelengths. And so this hidden population, or you can call it hidden, essentially quadruples the number of candidate clusters that we think are incredibly young, with incredibly high dust extinction and are very massive. And just to zoom in here, this is this sort of lower arm of the Western disk. And you can see that there are these arrows essentially point you to regions that looked incredibly red in the HST imaging that we couldn't actually get accurate SCD fits, because the reason that they look so red is because they're essentially undetected in the UV. And by being undetected in the UV, we essentially could not characterize their ages and masses. And so again, now you see in the near infrared, these super red sources are just completely popping out. And we're now able to easily find them and identify them. And the hard part, or the next step, is actually attempting to characterize them. So here is actually what a color diagram for star clusters in the near infrared looks like. On the y-axis here is the two short wavelength NIRCam filters, the F150 and the 200W. And on the x-axis, we have the 200 again, and then our long wavelength F356W. These are all in AB magnitudes. And what I'm showing in blue and green are actually, up until this point, the best essentially stellar evolution models that we have. So these are simple stellar population models, which include contributions from both stellar and nebular emission. And these are essentially the grids of models that we use to age date star clusters in the UV and the optical. And so again, I'm showing what they look like here in the near infrared. And you can see that at very early times, between essentially 1 and 3 million years, or between 1 and 5 million years, these tracks are incredibly vertical. So which means any deviation from those tracks to the right, based on sort of a contribution from dust or extinction, means that sources that fall far away from the tracks at these very sort of red colors are very likely to be sources that are incredibly extincted, that have ages between 1 and 5 million years. And you can see that after 5 million years in the near infrared, we essentially lose any ability to age date star clusters. So if you want to age date star clusters that are older, you still really need the UV and optical data. But in those cases, there's no dust. So you can get away with using Hubble to age date your intermediate and old cluster populations. The near infrared is essentially really only useful here with these kinds of models at really early times. And so the next step, of course, is to have much more sophisticated models, is to self-consistently combine the photoionization and contributions from PAH and dust. And that is much harder to do than it sounds, because with only 3 parameters to fit being age, mass, and extinction, you only need a handful of observations to actually get a constraining fit. But by also including the dust temperature, the pH strength, essentially contributions from other dust features in the near infrared, you have much more, many more parameters to play with, and therefore you require a much more comprehensive suite of observations. And so the early release science programming goals was not designed for me to go in and find and do all this star cluster science. It was meant to be broadly applicable to lots of different science that the community might find interesting. So we only got these wideband filters, and we only got these and another one, F444W. So we only had 4 filters, and the 444W filter is essentially dominated by dust. So you're getting very little information about the stellar populations. And so with the simple fact is we don't have the coverage in the near infrared to make really constraining estimates of age and mass for any one of these individual sources. But essentially, this box is our way of isolating the region of the color space where our youngest, dustiest sources are likely to live. And so if you essentially say that you believe this population of sources are your extremely dust-buried sources, what we find is that all of these points in gray actually correspond to these points that I'm showing here on the right-hand side. So all of these super red sources that you saw pop up in that movie that I just showed you with HST, all of those sources essentially lie at the upper right-hand side of this box. And so the motivation there is that we believe that at least broadly speaking, with the colors available to us in the ERS, we've identified this hidden population. So to come back to the diagram I showed before is, okay, where do we think the diagram is going to go? At early times, do we think that the age distribution is going to continue to increase or essentially drop off? And actually, if you were to take those gray points that I showed you in the previous slide and attribute them as young sources, what we essentially do here is we take our data from before, which is incomplete, and we add the contributions from the near infrared detected sources. And when you do that, you find that the power law slope is broadly consistent with what we found with HST over the course of the whole galaxy. And so at least preliminarily, it seems that the age distribution for at least this one system looks like essentially unchanged from 1 to 300 million years. And this is obviously subject to lots of uncertainty with how to actually individually age date clusters, and then having many more observations of more galaxies to say if this is something that we see ubiquitously, or if we see a lot more variation at the early times than what we're seeing with just one system. But this is essentially our first attempt to actually find and identify these very young buried clusters in luminous infrared galaxies. And then the next galaxy, the second galaxy that I'm working on, is NGC 3256. The beauty of NGC 3256 is that it's twice as close as VV114. So we have a lot more star clusters, thousands of sources that we detect in both the optical and in the near infrared that we can use to actually much better understand these different populations. In addition to the near infrared photometry, the difference with 3256 is that we also, instead of using the wideband filter, we actually use the 335M medium band filter, which is focused on the PAH. And so what our hope is that these boxes got slightly misaligned, but if you shift these up, these two boxes line up on the two nuclei, the northern and southern nuclei. And there's about 15 to 20 sources within those boxes that we detect in the near infrared that look incredibly red, that again fall in this part of the diagram where you might think that they're these incredibly red dust-buried sources. And so the hope is that with a sample of sources that we have near infrared photometry and we'll have near spec spectra and MIRI spectra, we should be able to actually calibrate how much PAH emission is coming from this F335M filter, and then what the ages of individual sources are based on their recombination line equivalent widths in the near infrared. Then we can use those ages and PAH strengths to calibrate these near infrared colors. And so in this paper, we're attempting to essentially improve upon what we did in VV114 by using the data directly for sources that overlap in both spectroscopy and near infrared imaging. And on the left is a color diagram of clusters that you might be more used to looking at if you look at star clusters. This is the UV and optical on the Y and X axes. And one of the things, the reason I showed this is just to highlight that if you look at, an AV of 2 vector here, by requiring UV data, we're essentially really only sensitive to things with AVs of 2 to 3. Whereas again, by going into the near infrared, we are sensitive to things that have AVs probably as high as 10, 15. So again, it's the window into this incredibly embedded population, which then allows us to study these early evolution of these sources to learn something about what the dominant feedback mechanisms likely are. So that is pretty much everything I wanted to talk about. I just wanted to highlight that these ERS sources have multiple papers and people working on them. The 2 that I was talking about are NGC 3256 and VV114. 2Zwicky 96 and the cluster is actually for 7469 in the ring, was published by Thomas Bond in 2022. And Sabrina Stierwalt is working on the photometry for 2Zwicky 96. And so in combination with these 4 sources, we also have HST mid-cycle program that I was awarded time to actually study 10 more galaxies, and I'm showing 6 here, that are being observed as part of the JWST GEO1 programs. And so we took a look at essentially everything in GEO1 that was going to be observed, and all of the LIRGs in the first essentially 2 years that didn't have UV observations, we essentially proposed for and got time on Hubble to obtain those. And in blue, I'm showing again the near spec FOVs. So all of these sources have either near spec or MIRI spectra that will accompany them in the central regions. And so again, with a much more robust sample of sources with near infrared imaging and spectroscopy coupled with UV observations, which we really need in order to find the sources that have emerged from their cocoons to separate the sources which are completely buried in dust, we're now going to be able to undertake a much more systematic survey of the embedded sources in the centers of these local LIRGs. And so this program I sort of called the belly of the beast, because we're really starting now to stare into the hearts of these really dusty systems, and we have not been able to do that at high resolution until now. And so this is where we're going. And the idea, of course, is that with not only detecting star clusters, but actually using the line ratios to infer something about what the dominant feedback mechanism is. So this is just an example of some simulations of star-forming clouds from the warp field set of simulations, where they just show that if you take star clusters at different points in their evolution, from very massive clouds to deeply embedded clusters to optically thin density bounded regions, or essentially low intensity star forming regions, you see that by looking at the line ratios, and this is again just the optical, we can do this as well in the near infrared. By looking at line ratios of ionized gas, you can really start to separate clusters in this parameter space by essentially what kinds of feedback is occurring in the surrounding interstellar medium. And so we're going to hopefully move beyond just identifying super red sources to actually identifying them, getting spectra for all of them, really characterizing them, and saying something about how they compare to the sources, the sort of really compact sources in other nearby starbursts. So that is everything that I have. I guess there's 10 minutes left, so I'll leave my final summary up, and I'm happy to take any questions that you have. Thanks for listening.
All right, thanks for an awesome talk. So if we could go back to your color diagram with your color tracks. So I'm seeing this large leap from 3 to 5 mega years. Would it be correct to say that that's kind of tracing the evolution of the most massive stars in the cluster that are sort of evolving on that time scale and dying off?
Yeah, thanks. That's a great question. I didn't actually mention it during the talk. This big vertical jump is due to the evolution of the red supergiants as they evolve. Essentially, once you get beyond 5 million years, the luminosity of those very massive stars essentially dominates the cluster at these very early times. And then once those stars go away, you're essentially left with the rest of the population that is very difficult to disentangle in the near infrared. But yeah, this vertical feature is due to those evolution of those those very luminous red supergiants. Yeah.
Very interesting. So could we then, is there any prospects for sort of flipping that around and potentially using these data to make inferences about the demographics of these very massive stars, or is it all kind of too degenerate?
This is too degenerate, but that is a great idea. I think what you would need to do is to get much more finely sampled data than this. And so this is a 4-band observations. What we really need is something like 6 or 7 bands to fully cover the near infrared, including recombination lines, including medium band filters for pHs. Because once you can disentangle the x-axis, because it's really the x-axis here that's very degenerate, because you have, on the y-axis, you have mostly stellar emission. And on the x-axis, you have stellar emission, dust emission, pH emission, all combined. And so if we could disentangle that, then yes, we could say something about the demographics of what the most massive star would have to be in those clusters. I think that's a really good idea. But we would need better data before we could do that. But it's not without a possibility. Yeah.
Cool, thanks.
Thanks. I have a question about the survivability of clusters.
Yeah.
So you said, yeah, it's very promising that you begin to form or like see this potential kind of something that could evolve into a globular cluster. But I think at the beginning of or the evidence you're seeing for the destruction is coming from kind of more environmental effects like YMCs and spiral arms. And so I just wonder, how does that slightly larger environment compare to what we would have expected for like the actual globular clusters we see around today in the early universe? And do we, have any dwarf starburst galaxies that we could study that may be more similar?
Yeah, great question. I think I think that the connection that I would paint is, as loose as you're saying, it's that it's really, we know the high redshift galaxies, their gas densities are higher, the clumps that they form are more massive, but there's certainly lower metallicity. And these galaxies are solar metallicity. So there's no getting around the idea that even if you could form something as massive as what you could form in a dwarf starburst at high redshift, the effect that feedback is going to have on the surrounding interstellar medium probably will be different because the ISM is of low metallicity. Galaxies are just way different than these sort of major mergers. There are dwarf galaxies that are being observed with JWST in cycle 1. And there's actually, I'm involved in a program that's looking at Hanai's 210, which is one of these well-studied nearby low metallicity dwarf starbursts. And we're looking at it with NIRCam and MRS to actually figure out, how much pH emission is coming from the massive clusters in there, how much potentially shielding do we think we're seeing? So all of those questions about how like a massive cluster like that could evolve into something like this, I think is still to be answered. I think it's more that, the idea that you have to have something that's incredibly compact and massive to survive. Like if something isn't very massive and compact, it will not make it from the early universe to today, regardless. And so that's, I think, what I was more trying to show. But yeah, the details of how LIRGs are actually like high redshift galaxies is, yeah, I think not perfect.
Any questions? Cool. Well, thanks, Sean, again. And Sean is here all afternoon, so if you'd like to talk more, the sign up sheet is in the email, or you can find Sean probably in the library when he's not talking to someone else. So thank you. Thanks, everyone.